In this video, we present a case that we have infinite number of solution for y equal g of x, and we'll determine the PDF of the distribution. Consider an example of y equal to a sine of omega t, where a is a positive constant number, and omega is also a positive constant number, and t is a random variable. So if you plot this curve of y versus t, so we have to solve y equal to a sine of omega t, so versus y. So I want to solve it. So usually I plot this one to get some idea. So if y is bigger than a, if y is here, or if y is smaller than minus a, there is no solution. So there is no solution for y bigger than a. So quickly I could say that f y is equal to 0, f y is bigger than a, means here and here the PDF is 0. For y is smaller than a, if y is magnitude of y is smaller than a, that means that if you are in this interval, you draw this line. Let's say this is your y. I draw this dashed red line here, and what you get is that this blue curve, sinusoidal curve, crosses the dashed line, and then we get the solution. So I get two sets of solution. One solution is here, the other solution is here. But these solutions, they repeat. So the red dots is not just one solution, so it's infinite number of solutions, but it's countable. The blue dot ones also are solutions, but they are having with a period of constant period. So let us try to find the solution. So I have to solve y equal to a sine of omega t. So if y is bigger than a, no solution. If magnitude of y is smaller than a, I have two sets of solutions. One is sinus inverse of y divided by a plus or minus. So this is, let's say, two solutions, this one and this one, and then you have multiple factors of k pi added to it and then divided by omega, so you have plus minus. So the plus ones are the blue ones, minus ones are the red one, or vice versa, doesn't matter. So what we need also to do is to calculate, we have this equation y equal to a sine of omega t, so I have to calculate dy over dt, which is equal to a cosine of, because the derivative of cosine becomes cosine of omega t, and then you will get a factor of omega here. So what I do here is that I write this as a omega, and instead of cosine, I put square root of 1 minus sine of omega, because I want to calculate absolute value of that, so I need to calculate absolute value of this guy, and then I could say this is sine of omega t to the power of 2, and then I could absorb this a, and then you could have an expression only in terms of y. So so derivative of y with respect to dt will become equal to omega square root of a minus y2. So you can easily prove that, and this is provided that y is smaller than. So if this y is smaller than this is non-negative and valid. So in that case, fyy, which is obtained by this fyy, is equal to summation over all solutions. That means over all these possible values, fx at any of these solutions that you see here. So this is one solution, and for pluses and for minuses, and then you could divide them by the Jacobian, which is d2 dy over dt, but expressed in terms of y, okay? So which is this one. So this is the distribution of the output, and you see that this is a complicated equation. Now, if this distribution of this random variable ft of t is smooth, okay, this can be approximated with a constant number, and then your distribution simplifies in this case. For the case that ft of t is a smooth function, this summation can be simplified, approximated with that, and then therefore in that case you could say that the distribution of y is equal to these curves. So if you want to plot this one, first of all we said that beyond a and minus a we have 0, so my PDF is going to be 0, so this is. Now, if you put y equals 0, you get the minimum value here, so you get 1 over pi a. And then if y becomes close to a, this becomes infinity, so you have a distribution like that. Okay, remember that this area, the area underneath of the PDF is equal to 1. So this is the PDF of fy of y, so the red curve.